Good afternoon, Internet. I am Matt Buyak, and in this video, I'll be looking at the 9th problem from the Project Euler problem archive. So in the last video, we solved this same problem using a simple C program and a brute force technique. But in this video, we're going to solve this problem using analysis alone. And in particular, we're going to use a technique that I showed a few videos back for generating primitive Pythagorean triples. So as you'll recall, this problem asks us to find a Pythagorean triple such that A, B, and C add to 1,000, and it asks us to find the product of A, B, and C. So let's get into it. We've already created our problem directory, so we'll open that, and in particular, we'll jump to our analysis file, and let's pull up the results from our the video I did on Pythagorean triples, and in particular, we want these equations right here. And I'll just add a note at the top here that the greatest common divisor of n and m is 1, and both n and m are odd. So we can start just by adding these three equations. As I just mentioned, we're trying to find A, B, and C such that A plus B plus C is equal to 1,000. So if we just take our results here and add them, then you can see, and in fact, let's write this as 2nm over 2 so that we have a common denominator across all three terms here. Then you can see that we have n squared plus n squared, so it's going to be 2 n squared, minus m squared plus m squared, so that cancels out. And then we have 2nm. Over 2, and you can see that this divides evenly, so that gives us just n squared plus nm equals 1,000. And we can factor that as n times n plus m equals 1,000. And so in general, our approach from here is just going to be to look at the factor pairs of 1,000 and see which correspond to solutions. And there aren't that many factor pairs. We could try each of them by hand, but we can do a little bit better than that, actually. So the first observation that we're going to make is that n is greater than m, and therefore n times n plus n is greater than n times n plus m. And note that this is equal to 1,000. And therefore, 2n squared is going to be greater than 1,000. And using our calculator here, we can just solve for n. We'll take 1,000 divided by 2 square root, and we get 22 and change. And so we know that n has to be greater than 22. We can also note, going back to this equation here, that n has to be odd. And so n plus m has to be even. And if we factor 1,000, you'll notice that that gives us 5 cubed times 2 cubed. And so n has to be a power of 5, because if n is divisible by 2, then obviously n is not odd. But we've already said that n has to be odd. And so we know that n is a power of 5. And so that means that in particular, because we know that n is greater than 22, that n equals 25 or n equals 125. So if we suppose that, suppose n equals 25, then we have n plus m is equal to 40. Note that I just took this equation here, set, excuse me here, it should be 25 plus m is equal to 40. So that was just, I just substituted 25 for n, and then divided both sides by 25. And that gives us m is equal to 15. And so from that, we can find our values of a, b, and c. Going back up to the top, back up here, you can see our equation for a is the difference of squares between n and m divided by 2. So that's going to be 25 squared minus 15 squared divided by 2. And so using our calculator, that's going to give us 200. So we have a is equal to 200. And so again, from our equations here at the top, you'll see b is equal to just the product of n and m. So that's just going to be 15 times 25. Gives us 375. And finally, we have c is the sum of squares, of the squares n squared and m squared divided by 2. And so that's 15 squared plus 25 squared divided by 2 is 425. Excuse me, I should write this out for completeness sake. There we go. And so it's pretty straightforward to confirm that this is in fact our solution. So that you can see the sum is 1,000, and if we take a squared plus b squared, and we take the square root, we get c. And so this is both a Pythagorean triple and a, b, and c sum to 1,000. So our problem statement here does indicate that there exists only one solution. So we could stop here. But you'll recall we actually had one more power of 5, or one more candidate value of n that we could consider. And so let's just see why that doesn't work out. And in particular, we had n times n plus m is equal to 1,000. But if we replace n with 125, you can see that that gives us 125 plus m is equal to 8. And so m would be a negative number. And so that's obviously not allowed. And so that does not correspond to a solution. So now just to finish up, we have our solution. The number that we have to provide the archive is actually the product of A, B, and C. So if we do 200 times 375 times 425, that will be our solution. As you recall, the answer to these problems always corresponds to a single integer. And so now we can go back to the archive and check that that does in fact correspond to the answer. So in the next video, we'll be moving on, we will not be moving on to problem 10 immediately. A few videos back, we solved a problem that involved generating prime numbers. And I promised you a follow-up video in which we would clean up our methods from that video and make them a little bit more robust in a way that we could use in the future. So in the next few videos, I'm going to be taking a look at some principles of good software design and using those to clean up our technique for generating prime numbers. So if that sounds interesting to you, then please check that out.